All right, so I'm Andy Sheinis. I'm head of instrumentation here, and I'm going to give you a quick overview of how spectrographs work. So this actually might be better called Basics of Spectrographs. You're going to have talks later this morning, or is it this afternoon, on high resolution, low resolution, and multi-object spectroscopy, which will go into the details more from a user standpoint. But I'm going to try and answer some of the basic questions that I think I might have had when I was sort of starting out in astronomy. So, the questions that I want to try and answer in this talk. Does this work? Let's see if I press.
It's the button right below the laser pointer.
Yeah, that's what I'm looking for. The red one. Yeah, there we go. Okay, so what's inside of a spectrograph? What are the parts? Why are some of them so big and some of them are not so big? What sets the sensitivity in a spectrograph? And how do I estimate, given a spectrograph, how do I estimate the exposure times in different observing conditions? Here we have a picture of an older spectrograph, which some of you may have used. This is A omega, which was built here. This is a new spectrograph that is currently being developed for Gemini, called the GHOST Gemini High Resolution Optical Spectrograph. That's what we guarantee. So, first question, what are the parts of a spectrograph? So, I'm sure you often see these pictures when people give talks about this sort of thing. Here's a sort of complicated looking ray trace for the Hermes spectrograph up at the AMT. And you can see we have some things labeled here. Collimator, slit, cameras, beam splitters. Some important bits aren't labeled for some reason. The gratings. So I'm going to talk a little bit about what each of these components are. And just, you know, as I also said, spectrographs can vary tremendously in size. This is a big one. You can see the main frame that we're putting together here done in a lab a few years ago. Here's one of these roll-away toolboxes. You can see this is very large. This hole in this piece of metal is for this collimated beam. It's sort of a meter tall. It's a big piece of equipment. Here's one of the BPH gratings. It's about half a meter. It's a half meter long optic. $120,000 worth of half meter long optic. Okay, so the important bits that go into a spectrograph. Well, you need a telescope, of course. Usually, you need a telescope. Telescope, just represented by a single lens here. It's much more complicated. Each one of these lenses that I've represented as a single lens, the components I've represented as a single lens are, you know, often large groups of things, but they fall into the category of, for example, collimator, which takes the image plane from the telescope and makes all of the rays from any individual field point, and field point is just the location of a star in the image plane. Makes all the rays parallel from any individual field point. Of course, if there's a different field point up here, they'll be parallel but at a different angle. There's a black box here called the disperser, and the disperser can be lots of different things. We'll talk a little bit about at least the most common kinds of dispersers. And then often, well, always in a standard slit spectrograph, you need to bring things back to focus. So there's a camera and a detector. And what the camera does is it takes the image plane from the slit and images onto the detector. And of course, you get many multi-colored images of that slit that are spread out. And that's the purpose of the disperser. I think that's probably all I'll say about that picture. So dispersers, I'll start with them since they are the most important part of a spectrograph. And there are several different kinds. Let's see. So we have gratings, which I will talk about in some detail in a minute. Reflection gratings. So gratings are ruled slits that allow you to interfere the collimated beam with itself. We can also have prisms, which, like the cover of Dark Side of the Moon, just uses the inherent dispersion in the glass to change the optical path length and spread out the beam in angular space. We have grisms, which are a combination of a prism and a grism. And those are often used to modify an existing spectrograph to allow us to get dispersion from a straight path. So you can imagine if I have an imaging camera here, a detector, and it's looking at the focal plane of the telescope. Whoops. I could, if I'm clever, insert an optic that would add a little bit of dispersion and smear the star trail. So if you've ever heard of objective spectroscopy or slitless spectroscopy, that's typically how that's done. Not necessarily with a grism, often just with a prism. A grism will give you more dispersion. So you guys will get a copy of all these notes downloaded, and I've listed sort of the important places to look for more information. Because this is an overview lecture, which is a condensation probably of about 4 or 5 different lectures. So maybe I should apologize a little bit for the volume of material. I'll try and keep to the important bits. So here's some pictures of holographic gratings. Holographic grating is what's in Hermes. And basically a holographic grating is exactly what it sounds like. It's a hologram. And it's a very simple hologram in that it's just recorded information from 2 flat interfering beams. I take 2 flat beams that are tilted at an angle. I'll get a fringe pattern, which is a set of vertical bars. And if I record that information in a grating and then illuminate the grating with a flat wavefront, it'll reproduce those two beams, which are split at an angle, which is exactly what we want to do with a grating in the spectrograph. An example of this idea of prisms, where we take a prism that has dispersion in one direction, it tilts the beam in one direction by a little bit, and then the grating tilts the beam in the other direction and has a higher dispersion. So for some wavelength that goes straight through, it spreads out the other wavelengths. You can read all about that in this reference if you like. So the other bit that was in that picture is the collimator, and as I said, I drew it as a single lens, but often it's made up of many, many different optical elements. Here's an example of a 1, 2, 3, 4, 5, 6, 7, 8 element transmissive collimator. This is something called the RSS, Robert Sobey Spectrograph on the South African Large Telescope. Sometimes they're made up of just mirrors, and typically it would just be a parabola. So here's Echelon Spectrograph and Imager on the Keck telescope, and it is just an off-axis segment of a parabola. Sometimes they're transmissive, sometimes it's a combination of both. So here's Hermes, and this is a big spherical mirror, and then we have some transmissive optics here and here in order to make the image quality come out good enough. So you might ask, why don't we just do the simple thing every time and just use a single mirror? It has to do with the size of the image plane, or the size of the slit plane. The bigger the slit plane, the harder it is for a single mirror to make good images all across the field. So if you have a larger field, you need to go with more optics, either transmissive or catadioptric, or in this case, this is a Schmidt camera, which we won't talk about. Okay, camera is probably the second hardest or most important thing, and that's the part that takes this splayed out, dispersed beam from the grating and forms nice, neat, crisp images of your slits or your fibers on the detector plane. Sometimes those images are a little bit blurry, and you'll probably hear all about that when it comes to data reduction workshop, how to deconvolve a point spread function. So cameras, there's lots of different kinds. They've been designing cameras for many, many years. If you go into space, often it'll be something called a 3-mirror anastigmat. It's just 3 mirrors that are used to correct the beam. Reflective cameras are good for wide wavelength ranges because of course, mirrors focus all different wavelengths in the same place, not the same for cameras. So if we want to do a camera with a wide field, we typically have to have a lot of different elements in order to both correct the shape of the image as it goes along from the center of the detector to the edge, but also to make sure that all the wavelengths focus either at the same place or at least in a plane. With a spectrograph, you can imagine if the wavelengths focus in a different place, you can tilt the detector to compensate for that, but they all have to come to focus on a plane, or else you'll have large blurry images of your slit, which won't be good. And then here's an example of a catadioptric. So catadioptric, if I didn't say so before, just means lenses plus mirrors. So this, for example, is the camera on the high-res telescope at Keck. This is the camera on the ESI, the high-res spectrograph at Keck. This is the camera on the ESI spectrograph at Keck. I forget what this anti-stigmat is to. Okay, detectors. Maybe well, also an extremely important part of spectrographs. Better detectors make for better spectrographs, both larger detectors and more sensitive. Initially, astronomers used this detector. It's only got a quantum efficiency of about 8%, so it's not so great. Plus, you can't integrate for more than a 30th of a second. That makes it even harder. So, lots of different kinds of detectors. Most of the visible detectors in astronomy are CCDs or CMOS detectors, and then in the infrared, we usually use Mercat telluride. We could do an entire course about detectors. I'm not going to talk too much about detectors, other than to talk a little bit about noise sources and the signal and noise equation in a minute. Okay, and the last major component of the spectrograph is what goes in the slit plane. So multi-object spectrographs have a large slit mask in order to block out all the stuff that's not important, all the sky that you can block out, and only let the interesting bits through in the slit areas. As I said, there'll be an entire lecture on multi-object spectroscopy. There will be another lecture on integral field spectroscopy. We could have a fiber system in the slit plane that relays the image from the telescope down to the spectrograph room, and it can do great things while it does that, like reformat a two-dimensional image into a slit so that we can use one of these sort of standard spectrographs. I think you have an entire lecture on integral field spectroscopy. Okay, so why are spectrographs so big? This is a question that always baffled me for a long time. So each one of these questions could be an entire lecture. Hopefully you'll get something out of this. Why are they so big? So here's a thought question for you. Here's a spectrograph on Sloan. Sloan's a 2.5-meter telescope. You can see an ethereal-looking hand here. Gives you an idea that this spectrograph, probably fits somewhere between the size of that bench and one of these desks. Here's another spectrograph that's on Keck. It's not a great image, but you can see a person here. So this one is about the size and oddly about the shape of a cement mixer. And it's, of course, much larger. And then here we have a proposed spectrograph for the TMT 30 meter. Here's a little person in here. This, by the way, is an image or a design drawing for this spectrograph, just to show you the size difference. So this is Demos. That's Demos. This is something that used to be called Moby. I think it's WFOS now or something. Who knows what they're calling it. I'm sure it looks much different. But the point is, we have 3 different spectrographs varying tremendously in size. They all deliver the same resolution, similar fields. Why do they have to be so different in size? What's the big deal? Hopefully we can answer that question. That is also related to the question of what causes dispersion. So the reason they change in size is because their dispersion requirements are different. They produce the same dispersion, but the beam going in is different. So I will state without proof that what causes dispersion, and I'll show this in a little more detail, but it's the optical path difference inside of the spectrograph of the interfering beam, where it's also the optical time delay that you can produce in an optical beam inside a spectrograph. So here's another thought experiment to ask you, how big an aperture? The aperture is kind of the characteristic beam size inside of a spectrograph, given by, if you look inside one of these mirrors, that's sort of the aperture size. We can't really see it here. We know the aperture size in here has to be small, because it's a small spectrograph. To produce a resolution of 100,000 in a diffraction limited case on a 10-meter spectrograph at 1 meter. Does anybody want to guess what the characteristic beam size might be to produce a resolution of 100,000, a very high resolution spectrograph at a 10-meter telescope in a diffraction limited case? 2.5 meters. That's a good guess. I believe it's 25 millimeters, and we'll see why in a minute. So thank you for guessing, whoever guessed. Okay. So this looks very complicated. Here's our picture again. I've bent things around a little bit, but here's our telescope represented by a single lens. Here's our slit plane, our collimator represented by a single lens. Now I've actually put in a dispersing element. I've put a reflective grating in here, and I've got a camera and a detector, and I've got some characteristic angles in here. The angle going into a grating is always called alpha. The angle coming out of the grating is always called beta. And I've simplified this equation from being just to make it more intelligible. There's the case in the spectrograph, if you've ever heard the term litro, it just means that it's symmetric. The angle in equals, the angle in equals the angle out, so it's staring back at itself. So alpha equals beta equals theta is litro. What you see is there's something called phi, and phi is the slit width. I apologize, somehow it didn't make it through to this drawing. But phi is the slit width in radians. R is the resolution of the spectrograph. D1 is this characteristic diameter inside the spectrograph, the collimator diameter, for example. D telescope is the diameter of the telescope, and 2 tan theta b is just 2 tan of this angle in the case where it's litro, so where it's symmetric. If it's not litro, it's a little bit more complicated because it has alphas and betas in it, but it's still qualitatively the same thing. So D1, 2 tan theta, if you think about it, is the optical path length difference from a ray that comes from the top of the grating compared to a ray that goes down to the bottom of the grating. So what it says, and if you were to take my optics course, for example, you get to derive that equation. It's not that hard, but we'll take it as given for this lecture. What it says is that slit width resolution product, and this is these are dimensionless, is given by the optical path length difference that you can get inside of a spectrograph divided by the telescope diameter. So it's this length minus that length divided by the telescope diameter. So something interesting. It's got the telescope diameter in it. The spectrograph knows how big the telescope is. That's kind of bizarre, but it's true. So this is the primary reason, at least looking at this equation, why spectrographs get bigger as telescopes get bigger. So if you look at this, the slit width resolution product is a dimensionless constant. So what it says is that given a resolution that you want to achieve and a slit width on the sky, if I want to take a spectrograph from one telescope to another, I either have to accept a lower resolution if I go to a larger telescope, or increase the beam diameter. Double the telescope diameter, have the resolution, or double the telescope diameter, double the beam diameter. So this D1 is a collimated beam diameter. It sets the scale size of the spectrograph, and it's actually, it comes out of the optical invariant called A-tan-Duke, for those of you who have taken an optics course, and the gradient equation. That's all you need to derive it. So let me do something interesting with this. Kind of interested in resolution for two different cases. So let me take the slit width. So this is in radians on the sky. This is a dimensionless number. It's microns per micron or nanometers per nanometer. And let's look at what happens in two limiting cases. One case where we have a seeing limited slit, and another case where we have a diffraction limited slit. So can somebody tell me what, when would we have a diffraction limited slit at a telescope? Actually, two obvious cases. I think it's not obvious so early in the morning, but space-based is one, absolutely correct. And what might be the other one? Amazing seeing. Well, if I have a small telescope and amazing seeing, yes, absolutely. That wasn't what I was thinking, but that's true. How do I produce amazing seeing at a site that's good but not dead space? Adaptive optics, exactly. So, diffraction limited, this is the case for space. It's also the case for adaptive optics. So in the diffraction limited case, the slit size is going to be at the diffraction limit of the telescope. Diffraction limit, qualitatively, there's a constant in front of here that you can ignore, but the diffraction limit is just the wavelength divided by the diameter of the telescope. I'm sure you've all seen that before. If I plug that into the equation for resolution, and plug this into phi and solve for the resolution, I find that what I get is, well, I still have this optical path length difference, but now the diameter of the telescope is gone. It's just wavelength. And what it says is the number of wavelengths that fit into that optical path length difference. So in a diffraction limited case, the spectrograph doesn't care about the telescope size. It only knows about the light. This is the equation I use to get that very small 25 millimeter diameter beam. In the seeing limited case, and this is where we probably spend most of our time observing, the slit width is equal to the wavelength divided by R naught. Does anybody know, has anybody heard of the Freed parameter, or R naught? It's a characteristic scale size of the atmosphere. So it's the scale size of the atmosphere at your site over which a telescope would be diffraction limited. So you can sort of imagine it as it's a cell size of a column of air that's completely undisturbed. So that the beam that goes through that is completely coherent and flat, and is not, it's not rippled or disturbed by the atmosphere. So if I do the same thing I just did and solve for the resolution, well, I get sort of the same thing. It's the number of wavelengths that fit into this beam difference, this optical path difference, but now it's scaled by R0 divided by the diameter of the telescope. And that scale size is basically the number of seeing cells that go across the aperture of your telescope. Now, what does that mean? Sounds great, but maybe we can draw a little picture to make it a little bit more obvious why that is. Okay, so in a spectrograph, I will also state without proof, what we usually do is we image the pupil onto the grating. The pupil is just, in most telescopes, that's the front, either the secondary or the primary, and it's the input aperture for the telescope. So you can imagine that I have the input aperture, a little picture of the input aperture of the telescope here. If I could put a piece of film in here, I would see the spiders and the shadow of the secondary. And if someone was standing at the edge of the platform with their hand in here, I'd see a little shadow of the hand. What also is imaged onto the aperture of the grating is the distribution of the seeing cells inside of the telescope, where it's actually the integrated seeing cells looking down the optical path. So you can also imagine, that there are a series of seeing cells here that represent the seeing cells at the telescope. So over this seeing cell, the beam is pretty flat and straight. You know, if I had a tiny little telescope and put it here, I'd get a diffraction limit image. Likewise here, here. But if I tried to connect this to that, I wouldn't be able to do it. And the reason for that is that the beam is not laterally coherent across the entire aperture, which means if I have a wavefront right here, and I know what the phase of that wavefront is, or if I have a photon right here, I know what the phase of that photon is, and I want to look at one over there, I can predict exactly what the phase is. That's coherence. The wavefront or the phase of the wavefront is predictable across that surface, or the two photons are propagating at the exact same phase. If I have a wavefront here or a photon here and one here, I'm completely unable to predict the phase, so they're not related, which means they won't add coherently. So what it means is that the resolution is defined by the number of wavelengths that will fit inside of this optical path difference only over the coherent beam. Think about the coherent section of the beam. What I'm doing is I'm interfering, a ray from here, or a photon from here, and a photon from here, and I can differentiate the wavelengths by exactly one wavelength. So you can imagine, one way to think about it is I've got a photon here traveling with some wavelength, and I have another one here traveling with a slightly different wavelength. I can resolve the separation in those wavelengths when they're one wavelength apart over this entire beam, which is the exact same thing as saying that the resolution is equal to the number of wavelengths that fit into these two optical path differences. So these blue brackets show you the physical path difference. So that's why spectrographs need to get really, really big on big telescopes. The seeing cell size doesn't change. A small telescope at a site, I'll have 4 of these seeing cells across a meter telescope. And a 10-meter telescope, I'll have 40 of them. So the atmosphere doesn't change, the telescope does, but I'm still imaging this then. So if I had a very small telescope and just had 4 of these, I'd get to use more of the grating. So this is the case in diffraction limit. The beam is coherent across the whole thing, so I can interfere from the very top of the grating down to the very bottom of the grating. Here I've given you the true optical path difference just using the gradient equation, where alpha is the input angle, beta is the output angle. In the litro case, the characteristic angle is alpha equal beta equal theta. But what it means is you get much more dispersion out of the same size. So it took me a long time to figure out physically what was going on. So I'm not surprised if you don't quite fully embrace it, but that's fine. The important thing is, if you've ever heard of something called the grating resolution, that's the maximum resolution the grating can deliver. That means that it's the coherent beam across the entire grating.
Can I just ask a question?
Absolutely.
So basically, for an Earth-based system, in time, that's changing all the time. Your resolution is changing all the time.
That's true. So the individual coherent cells are moving across the grating, and they're changing the locations of the things that interfere. But what we're actually doing is each one of these cell images is interfering with itself, and that image of that interference, which is the slit, is being imaged onto the detector, and each one of these individual patterns is being imaged incoherently on top of each other. So all those little images, if you were able to separate them somehow and look at them, you'd see them getting dimmer and brighter as they go off the edge of the grating. But they all fall on top of each other. That's the job of the camera. Hope that makes sense. So this is the diffraction limited case. This is why spectrographs that are used with adaptive optics can be smaller. This is why spectrographs that go into space can be smaller. So I think here's the conclusion for that section. One way to think about spectrographs, the resolution is not a function of the spectrograph or the optics. It's a function of the property of the wavefront that you put into the spectrograph. This optical time delay or optical path difference that's available for the interference in the coherent beam is what sets the resolution. The job of the telescope, the optics, the AAO system is to provide as much OPD as possible and collect that information. So it's a property of the light going in. So I said that I alluded, well, we used one example here. That was just this reflection grading using litro. But it works. You can use quantum mechanics if you're a good physicist and derive this in terms of the optical time delay for anything. So it works for prisms. It works for other dispersing elements, but it's the same rule, and it's given by quantum mechanics. It's not from the geometry of the spectrogram. All right, so how do you get a long time delay? Well, you can use a long grading. That's called a shell. Shell, I think, means staircase in French. Is that right? French speaker. You can use, well, here's the other thing I wanted to point out. So this delay is actually not the physical distance. Listed as a physical distance, but it's the distance the light travels. And light, as you know, travels a longer distance if it's in a medium. So if I were to fill this with a high index medium, I get a longer path difference. So that's what an immersion grading does. In the old days, you would literally take this area, build a cell around it, and fill it with oil. But now we have silicon immersion gratings for the infrared. Silicon, I think, in the near infrared has an index of 4, which means you get 4 times the dispersion for a given path. So we can use high index materials. We can make a big beam. We can do all of the above, which is what, for example, is being done for, there's an infrared immersion grading, giant infrared immersion grading spectrograph for GMT. I never get the name of it. For Hycrin? Hycrin? Yeah. That doesn't sound familiar. Well, anyway, people are doing all of the above right now for GMT. Some of you will probably observe with GMT. Maybe you'll remember this lecture when you observe that telescope. Okay, so what are shells? I mentioned this shell. They're, of course, precisely ruled gratings, a few groups per millimeter. They're used at high angles. That means they're tipped over very far, so you can get a long path difference. And in fact, so I have to apologize for this. I have to apologize for optical engineering nomenclature, but there are 2 things called R. R is the resolution, but for spectrographs, R is also this is equal to 10 theta. So when you hear of an R4 spectrograph, it just means it's used at a tangent angle 4. R2 is shallower, R1 is shallower. So theta B is big because it's at a high angle, 63 to 78 degrees. They're high orders. So you might be using something from n equal 100 to n equal 600, depending on the spectrograph. Or an echelette just means it's lower order shell. They have high dispersion in a compact package, high 10 theta, high throughput, good blaze efficiency over a wide wavelength range, nearly free of polarization effects. Disadvantages: they're hard to make, they're expensive, the orders overlap. So if I just took a collimator and a camera and imaged that interference pattern from the shell grading, I would have a mess because I'd have all the orders on top of each other. That's why we have cross dispersers to spread out the different orders.
Just to say that sometimes that's an advantage actually having overlaying orders. Just can actually build up the signal. That's what I'm doing.
but the different orders have different wavelengths landing in different places. So I'm not sure how you build up the signal when you can't separate up. I mean, one thing you can imagine that people may do in the future, instead of cross dispersing, they'll use wavelength selecting detectors, so that you'll know which order you're looking at just from, where in the well the electron comes from. Well, we can talk about that afterwards, because I don't understand how that works, but I'd like to know. So if you don't cross disperse, you can use order blocking filters. Of course, cross dispersing is good with a two-dimensional detector, because it makes efficient use of the detector. Here are some pretty pictures that everyone's very, very familiar with. This is sort of a pseudo-color picture, of course, but here's a high-resolution image of some solar spectrum, I believe. This is high-res, actually. But I could be wrong. Anybody pick out their favorite lines here? This is calcium H and K. Okay. So here's another shell. So one thing I did want to point out, the free range is proportional to 1 over the order number. So what it means is the length of the spectra change as a function of order number. If you're at high order number, it looks very linear. If you're very high order number, it almost looks like they're the same length. But what you're actually doing is you're collecting a portion of the image. So this, for example, shows maybe the full bandpass that a given spectrograph might produce, but often detectors are smaller than that bandpass. So this particular system shows a detector placed here for one band, and then you physically move the image of the echellogram by changing the grading angle, and then put the detector here and the detector here. It's better if you can capture the entire spectrum. When you're using an echelle or echelette, it's in lower order numbers. So this one's going from order 5 to order 15. So the 1 over n length looks much non-linear, which means it's less efficient use because you're not using these edges. But there is light that lands over here. It's just not super efficient. So this part of this order is the same wavelength as that part of that order. So you can go at and take a read noise hit. So some numbers. This is just filling in numbers for different situations using that equation. So an R2 spectrograph with a resolution of 50,000 at 1 micron on a 2.5 meter telescope. So this is the answer to my first question. I showed you the picture of Sloan, 150 millimeter diameter collimator, the 10 meter aperture. Sloan doesn't give you 50,000, but you get the idea. 10 meter aperture would be 600 millimeter beam diameter, and the 30 meter would be almost 2 meters. Giant spectrographs for seeing limited. For the diffraction limited, it would be 12.8 millimeters for all of them. Any telescope. Here's an argument for adaptive optics right here. There are many other arguments for adaptive optics, which you will hear about. How am I doing on time? Okay, we've got about
20, 15.
15 because we're going to leave 5 for questions. Okay, what sets the sensitivity? Do we have any questions so far? It's a lot of stuff to take first thing in the morning. Okay, spectrograph speed. The number of counts per second per angstrom. There are 3 cases we generally look at in astronomy. We have the case where we're slit limited. The slit blocks some of the light on all edges of the slit. We have an intermediate case where we're slit limited in one direction, and we're object size limited in the other direction, and we're image limited is the 3rd case. So, can someone tell me what this situation might be?
diffuse source.
A large diffuse source. Maybe nebular spectroscopy, looking at a galaxy or a nebula. What case would this be? This is a star image. Now, in reality, this is a star image if we're looking at a spectrophotometric standard, because we're not cutting the edges of the star image at all in a very oversized slit. Usually what we wind up doing is cutting down the size of the image a little bit in order to get more resolution and most of the light through. And then the intermediate is sort of in between the two. In reality, when we observe stars, sort of in the intermediate region. Okay, so the speed is set by, in these three cases, if we are slit limited, it's set by the area of the grating, or actually the area of the slit. In the intermediate case, the speed is set by the diameter of the telescope in one direction, and the width of the grating, or the width of the slit, in the other direction. And in the image-limited case, it's set by the area of the telescope only. So that's actually kind of interesting. If I'm looking at stars, of course, I can go much deeper with a larger telescope. If I'm looking at an optically dense source that completely fills my slit, the telescope diameter doesn't set the speed. I get the same number of counts from a 10-meter telescope as I do from a 1-meter telescope. How many people don't believe that? Well, okay, it's actually true. So what the telescope does, so first of all, this is, the speed is the counts per second per angstrom from a given size on the detector, physical size, square microns. So if I have a pixel on a 10-meter telescope, it occupies a much smaller space on the sky than a pixel on a 1-meter telescope. I get the same number of counts because I'm looking at a smaller segment of the sky with the 10-meter telescope. So the scale size completely compensates for the telescope size change. Hopefully that makes sense. That is a product of the optical invariant, A10-do. And we won't get to it in this discussion, but at the end of the notes, there's a couple of slides about A10-do and surface brightness that will hopefully prove that to you. Okay. So I state this without proof, given the amount of time that we have. How do I estimate the exposure time on the spectrograph in the system? So I'm sure everyone's seen this. You should have it tattooed on the back of your hand somewhere. 10 minutes. Okay, thanks. So this is your old friend, the signal and noise equation. And if you haven't seen it, you should become intimately familiar with it. Because it's always, this is what goes into the exposure time calculator when you go to the telescope. And if there are assumptions in the exposure time calculator that do not apply to your particular observing situation, you might want to do a back-of-the-envelope test, a check to it. So what it says is that the signal is just the rate of photons falling from your star times the integration time, and then the noise is the sum in quadrature, so the sum of the squares of the noise. For photon noise, the photon noise is the square root of the signal. So the square root of the signal squared is the square of the noise. So there it is there. The noise from the sky is just the square root of the number of sky counts. And if I square that, then I get R sky squared times T. Read noise is not, read noise is a linear term, it's not a square term. So to get the square, I have to add it in here. And then there's a gain term. And then the noise in the dark current is just equal to the square root of the number of counts in the dark current. And then I square it, so I get dark counts squared. This is the basic noise equation that includes noise from the The source, shot noise in the sky, read noise from the detector, and dark current. There are lots and lots of sources of noise that are not included. Those mostly enter in terms of scattered light and light noise that's not in this equation. And then if you have detector noise that's also not in this equation, you can have fixed pattern noise in the detector, which you can't just subtract the noise term from the fixed pattern because it's not necessarily predictable with exposure time. Let's see. I wanted to jump to the. Okay, so the limiting cases for bright sources, the signal to noise is just proportional to the shot noise in the source. So it's really just proportional to the square root of the integration time. It's the signal in the source divided by the noise in the source, which is just the square root of the source counts times the square root of time. If you are read noise limited, so in other words, if your exposure time is so short that you don't have enough counts in the sky or in the source to be greater than your 2.5 electrons of read noise, just to pick a number, it could be 2.5, it could be 4 or 5. In the infrared, it might be 20. But if your exposure time is so short, or if your dispersion is so high, so the signal that you have here is per detector element, and in the spectrograph, we've dispersed the light. So the higher the dispersion, the fewer photons from the sky and the fewer photons from the source. So a super high resolution spectrograph will often be read noise limited unless you're looking at 8 magnitude stars, which is why we look at bright stars at high resolution, but also because they are scientifically very interesting. And then in the case where you're sky limited, then it's the noise in the sky that dominates. This, also a function of the square root of time, but this is now the signal in the star divided by the square root of the number of pixels and the number of sky counts per second. Okay, so now backing up. Okay, so how do I calculate the number of photoelectrons per second on my detector? For a resolved source, you're measuring surface brightness, and the energy is just equal to the A-tan-do, which is the area times the angle. So it could be the area of the telescope and the angular subtents of the detector, or it is the area of the detector and the angular subtents of the beam coming in. The funny thing about A-tan-do, which is also a nice lecture all by itself, is that it's conserved everywhere in the telescope. Doesn't matter if I look at the front of the telescope, take the area of the telescope times 1/10 of an arc second squared for a small pixel times this I nu, which is the surface brightness. That's the energy, and the energy is divided by h nu is the number of photons per second. Doesn't matter if I do that at the front of the telescope or in the detector plane. So I'll just state this for an infrared source, an extended object. It's easy. Ironically, you only need 2 things. You need to know the temperature of the source, the quantum efficiency of the entire system, the resolution, the size and angle of the beam coming into the pixel. You don't need to know the telescope aperture, the F number, the slit size, anything. All you need to know. 4 minutes? Okay. For an extended object in the visible, you need the surface brightness of the source, the system losses, the resolution, and this A omega, the area of the pixel and the angle of the beam coming in. You also don't need the F number, the slit size, or the optical term. This is also a product of, or a corollary to my statement earlier that for extended sources, you don't need, the size of the telescope doesn't change the signal. So we don't need to know the size of the telescope in order to calculate the signal. For a point source, however, we're measuring the total flux. So we need to know the area of the telescope, flux in the source, and the integration time. For an unresolved object, in order to get the flux in the source, you need the source magnitude, telescope aperture, system losses, and resolution. And I throw some examples in here that will be in your notes to check against. I talked about that. These are the things that are missing. Some of the things. There are many, many, many things that are missing. Relic radiation from the Big Bang, integrated light from unresolved extended sources, thermal emission from dust, starlight from dust, solar light scattered, zygo light, line emission from galactic nebulae, line emission from the upper atmosphere, which is air glow. Spend a lot of time worrying about that. I'm sure you'll have an entire workshop about how to subtract OH lines, right? Thermal noise from the atmosphere, sunlight, moonlight. Moonlight, of course, is probably the largest source of scattered light. Man-made light scattered into the beam. Oftentimes we discover that there are LEDs inside of our spectrograph. We don't discover it until we take it to, well, hopefully we discover it in the lab. Sometimes we discover it at the telescope because things change. And then maybe one of the more important and harder things to model, but certainly there's thermal or scattered light from the telescope dome instrument. Okay. So this was my example from thermal imaging. Resolution 5,000, pixel size 10 microns, final focal ratio f3, source temperature 5,000 degrees, operating here 2 microns. All you need to know is the surface brightness, which you get from the blackbody curve, the A omega of the detector, which is given by the 10 microns is the area, the f3 gives you the solid angle, the QE of the entire system, so that's not just the detector, that is the absorption by the telescope, absorption by the spectrograph, etc. And then the delta lambda over which you observe, that's the spectrograph resolution. You can put it all together and get the number of photons per second, or the total energy in watts divided by h nu gives photons per second. I've done the same thing for source and the visible. I leave it to you folks to check my work after class. I think somehow this is the one you always do in astronomy because it's the most common one. This is for stellar images, but I left the calculation off, probably as an exercise to the student. But you need the source flux, the area of the telescope, the QE of the entire system, the resolution or delta frequency over a pixel, and the integration time. You get the flux from the magnitude equation, the number of photons from E over h nu. And we did a calculation as an example, surface brightness of the moon, how many counts you get from the moon. And I think that's it. So, thank you.
You've got plenty of time for questions.
Plenty of time for questions.
Thanks so much. Does anyone have any questions for Andy? Questions, comments, concerns?
What are you working on right now?
So, unfortunately, I'm the head of instrumentation, which means I don't get to do an awful lot of instrumentation myself. So I'll tell you what instrumentation is working on, and I'm nominally involved with it, but I don't get to spend as much time in the lab as I used to and as I like. So we're building this system for Gemini, which is the high-resolution optical spectrograph. That's a fiber-fed spectrograph that'll be done in the Peer Lab. 2 resolutions, 50,000 and 75,000, and it'll be fed by a fiber IFU, actually a pair of fiber IFUs. So in the low resolution mode, we can do 2 objects in parallel. High resolution mode, just a single object. And we use this equation to make a smaller spectrograph than you would expect for a 10-meter telescope. Here we go. So we are at an 8-meter telescope, but what we've done is we've sliced, this is what an image slicer does. We've sliced the image, so the slit width is equivalent to a much smaller telescope. We slice the image basically into 19 fibers. I think that's 7 across, so we have 1/7 of the slit size, which means we can reduce the internal diameter to 1/7 of what it would be if we fed the straight image to it. So this is one of the advantages of fibers or image slicers. So in addition to that, we are part of the Foremost project for ITSO, and Foremost is an effort to reconfigure the Vista telescope to be a dedicated, super high number of multi-object spectra over a wide field. So I think it's 2.5 degrees and 2,500 fibers with medium and high resolution spectrographs, 2 different spectrographs, and that will occupy the entire facility. That's all it will do. So we are providing the fiber positioner for the Vista telescope, and that allows us to be part of the Foremost consortium with significant scientific access. Maybe not the same access as all of the ITSO members, but we get to lead one of the surveys, the WAVE survey being led by Simon Driver. So anybody in Australia will have access to the WAVE's data. And then there are 8 researchers in Australia, the Foremost 8, who have access to all the data. And I think that Dan is one of them. Is anybody else in the room one of the Foremost 8? Maybe not. But you can look up on our website and see who they are. In addition to that, we are building a Taipan spectrograph and positioner for the Schmidt telescope at Siding Springs. And Taipan will be a 500,000 galaxy survey measuring detailed velocities to try and beat down the noise in H0 to 1%. And it uses our new nifty Starbucks technology, which I think
Tyler talked about.
Tyler talked about Starbucks?
He actually, if you do see him around, he's volunteered to take any and all Taipan questions.
Okay, good.
So, and we heard a little bit about the hoverboard from Michael yesterday. And, so there's some very.
So we have some R&D stuff, the hoverboard, and we're looking at putting wavefront sensors in Starbucks for tomographic reconstruction of the atmosphere. You know, every field you look at, your star image, your guide stars will be in different locations. So if you can reconfigure those on the fly, that'll allow you to have a much more versatile adaptive optics system. OH suppression fibers that were built at University of Sydney have not yet been fully characterized. We're building a new infrared spectrograph in order to try and measure the rejection ratio of the OH fibers. That's called Praxis.
I think it's a pretty big list. Maybe refer everybody to online.
I can do that.
See
We could stay here for the rest of the hour.
if you want to talk to me about it, maybe during coffee. If there's an extra question now.
I just want to touch on photonic spectrographs. That's just why breaking this nexus.
Absolutely. So here's the other thing. Diffraction limited. So photonic spectrographs are diffraction limited by their nature because they're being fed by a single mode fiber. A single mode fiber means light is propagating in a single mode, and single mode means diffraction limited. Photonic spectrographs are spectrographs in an extremely small package because they're diffraction limited. And the idea is that rather than interfering in free space, the way we've done here, I interfered, trying to interfere this part with this part. What a photonic spectrograph does, this is all a solid piece of glass, and there's a little channel cut in the solid piece of glass. So I have a series of channels that are in parallel, each with different path lengths. So I physically control the light from a single field point to a single fiber, and then I still need a camera or some focusing element to image them all onto a detector. And instead of producing an optical path length and grading, I have sort of single channels that have been optically machined into a piece of glass that serve as the individual grooves in the grating.
Very
And
cool
that's
stuff.
how we get a diffraction limited performance.
Are you going to be available at coffee for questions?
I'll hang around to get coffee for questions. Yeah.
All right.